So then second step I will quickly sweep through because time is short. Recurrence, that you first select a minimum earthquake magnitude beyond which it is expected that that earthquake is going to produce some damage. Generally it is 4. We assume for structural applications that any earthquake which has a magnitude more than 4, in some studies it is 5 also, but we assume that a magnitude more than this is going to affect our structures. So we gather all that data either from instrumental records, either from historical seismicity, historical records, or either from the paleoseismic investigation, and then you finally make an earthquake catalog. So earthquake catalog is a list which tells us that this much magnitude occurred in past at this epicenter location, this depth, this region at this time, right. So it's a detailed list of all past earthquakes in your area. This is another example of an earthquake catalog. Obviously this will be a detailed list containing thousands of events, but you can see here for example the source from which this data or this earthquake is included in this catalog, the year of event, month, date, hour, lat long of the epicenter, then depth of that earthquake, and then magnitude is recorded in which magnitude scale, Richter, body wave and surface wave, or maybe moment magnitude scale, and then some other information about that earthquake. So catalog is a list which you develop for your study area containing all that information, and you go for all international sources, databases, historical records and paleoseismic studies if they are available, and finally make a comprehensive list, and your future prediction for earthquake will be as reliable as the reliability of this catalog, because this is the basis. This will be processed in a statistical engine to finally come up with the future prediction, right. So if this is more accurate, the future prediction is more accurate. If you have some false events or wrong epicentral distances or locations or depths, wrong magnitudes for example in that list, or duplicate events or dependent events like aftershocks, foreshocks, your prediction is going to affect in an adverse manner. So this is an example of how seismologists actually carry out excavations in existing faults to see how they slipped in past hundreds and thousands of years, right. So different layers here you can see, they can be studied to have an idea about what magnitude earthquakes would have produced. I mean they were produced in past. For example, you can see that this line is a signature of one slip, right. This can be studied, this can be evaluated by seismologists to come up with information about past prehistoric earthquakes and some rough estimation about their magnitude also. So you can see here that this is a signature of a thrust fault, and then you can study these layers to actually calculate how much slip happened at that time thousands of years ago, right, and then convert them approximately into magnitude and include it in our catalog. That example is from Taiwan, this is from Thailand. Then finally you come up with this kind of a visual representation. This is that same list of earthquakes now shown graphically, right. So you can now classify earthquakes in different manner. In this representation, for example, all blue dots are from AD 10 to 1900 CE, historic earthquakes. Obviously the instrumental records were not available, so they are all from historic data, right. And you may have one observation that all blue dots which are historic earthquakes, they are all large magnitude, because the size of that dot is telling you how much is the magnitude. So they are all approximately magnitude 8 or above. Why this is so? Obviously yes, that it is difficult to miss a large magnitude earthquake in historical records. Obviously they caused destruction and therefore they were mentioned in those records, right. So it is easy to miss a magnitude 4, 5, 6, but it is not easy to miss a magnitude 8 in your any historical text, right. So all of them are large magnitude, but then you also have 1900 to 1964, these you can say green dots, and then after 1964 up till 2018. The size of the dot here is showing you the magnitude, and the color is showing you the time at which that earthquake occurred. Another representation of the same earthquake catalog, but now the color is showing the depth, right. So deep earthquakes are green color, they are mostly located in Hindu Kush region. Shallow earthquakes are spread along the main plate boundary and along the main faults in Pakistan, right. Red are intermediate, can be called intermediate. Again, the size of the dot is magnitude. Now this is how you construct the magnitude recurrence relation in stage 2 as part of the PSHA process for each seismic source zone or area source or fault. For each source you get this kind of an data from the catalog. So you say that for this particular source I have magnitude 8 one number of earthquakes in last 100 years. Let us say we have a catalog for 100 years. So capital T is 100 years. So we say that in those 100 year data, magnitude 8 occur one time, magnitude 7 occur 7 times, 6 occur 80 times, 5 occur 1000 times, and 4 occurred 6000 times. So this is the total number of earthquakes which are enclosed in one area source or which are attributed to one fault line, right. So this is literally counting the earthquakes from the catalog, right. Then you divide them with the total, because this n of m simply means number of earthquakes of a particular magnitude in last 100 years. You divide them by 100 years, it becomes the annual n of m, right. In one particular year, these much earthquakes of these much magnitude occurred in past 100 years, right. Then you take cumulative, like 0.01 can remain like this, but then you can add 0.01 with this 0.07 and get 0.08, then add this with this, you get another number, add this with this, another number. This is a cumulative annual n of m. Now cumulative means magnitude that much and more. For example, now this 70.88 simply means that in one past year, any one year of the past, these much number of earthquake occurred having magnitude 4 and above. And above means that it is cumulative number. Similarly, this means magnitude 5 and above, right. So we get cumulative annual n of m, right. So we can plot any of these 3 columns on y axis with the magnitude on x axis, and it will be called as magnitude recurrence relation, right. So there are different forms of MR relation. We can plot directly the number of earthquakes, we can plot the annual number of earthquakes by just dividing the whole y axis with the total number of years for which the data is there, and we can also have this cumulative annual n of m on y axis. So in this particular example, obviously this is increasing with reducing the magnitude exponentially. So we may have a log of the y axis is the log scale, right. So 0.1, 1, 10, 100, 1000, 10,000 like this, right. So if we have log scale on y axis and magnitude on x axis, the data will show a linear trend, right, because this is almost of the order of 10, 1, 7, 80. So every time roughly the number increased by 10 times, which means that when you have a log scale on y axis, you get a linear line, right, because the trend is linear, but it is declining. As the magnitude is increasing on the right hand side, the line is coming down. So the number of earthquakes of each magnitude, they are reducing exponentially. Now if we plot the last column on y axis, because now currently what it simply means, it says the magnitude 8 earthquakes in this particular seismic zone or source, the number is around, let us say 3, right, or 4. So magnitude 8 earthquakes occurred 4 times in last 100 years, let's say. But if we have the last column on y-axis, we can say magnitude 8 and above, magnitude 4 and above. The number will mean that magnitude and above, right, because we take cumulative. So 8 number will be same, but the 7 will be 7 number plus 8, right. So it will be cumulative. So n of m, annual n of m, the middle column is called annual occurrence rate. I mean, this is the number of earthquakes which have occurred per year in past 100 years, right. So on average, magnitude 6 earthquake, 0.8 earthquakes, number of earthquakes occurred in 1 year on average, right. There were 10 earthquakes per year which occurred of magnitude 5 in last 100 years, right. So the middle column is annual occurrence rate, annual occurrence rate. The last column is cumulative annual n of m, which can also be called as the cumulative annual frequency, cumulative annual frequency, and also can also be called as the annual frequency of exceedance, because this number tells us that what is the number of earthquakes per year which have occurred in past of a particular magnitude and more, particular magnitude and more also. So it is annual frequency of exceedance, which is also called as annual rate of exceedance, right, frequency of exceedance or rate of exceedance. So all of these terminology should be very clear, but actually it all started with just counting the number of earthquakes for each source and their magnitude also, right. So just see that the probability of having an earthquake with magnitude equal to 6 in next 1 year, see the same trend we can assume for future also. The plot is plotted for past data, 100-year data. So the annual n of m actually means past 1 year, right, any of the past 1 year. But let's say magnitude 6 is this one. I go up and I come up with a number. From table I can also see that this is obviously, this is not corresponding to that table. This is just one example. For magnitude 6, the number is 0.88, which means that the possibility of having in any one future year having a magnitude 6 or more than 6 is 0.88 or 88%, right. But this number is telling you that only magnitude 6, this number is telling you 6 and above, right. So I can simply say that the probability of having an earthquake with magnitude 6 in next 1 year, because it is the annual number, next 1 year is 80%, 0.8. But the probability of having an earthquake with magnitude 6 and above is 0.88, which is 88%. Now this last number 88% is also known as probability of exceedance. The probability, annual probability of exceedance actually, that the probability that this magnitude will be exceeded in next 1 year, right. Now this is one common law which is called GR or Gutenberg-Richter relationship. It is a mathematical equation or model to fit to the MR relationship. We have seen here that generally the earthquake reduce exponentially, which means that if we can have a log y axis, the line will be a straight line, and the straight line equation we already know, and that is a minus bm, where a is actually the y intercept, this number on y axis, and b is actually the slope, and m is actually the x axis, which is the magnitude, right. But on the left hand side we must have a log of any quantity on y axis. It can be n of m, it can be the middle column, it can be the last column, right. In all three cases the y axis will be exponential or it will be log scale. So based on this straight line assumption, Gutenberg and Richter proposed this mathematical equation for the magnitude recurrence relationship. Generally, what we actually do is, for each earthquake, for each seismic source, we plot these black dots, because each black dot is actually what? It is coming from the data, right? So, I will have 1, 2, 3, 4, 5 dots on this line. Actually, first I will have 5 dots, and then I will select a straight line which will best fit those 5 dots, right? And then that straight line will have an equation which will be of this form: log of y is equal to y-intercept minus slope times x-axis, right? So, this 7.7 is actually y-intercept, 0.9 is the slope of that line, capital M is the x coordinate or magnitude, and log of n is the y number. So, this is the straight line equation proposed by Gutenberg Richter, both of them actually, and based on the large earthquake data sets, they concluded that whenever you plot this MR relationship for any source, roughly they can be idealized like a straight line going down if you make the y-axis logarithmic. So, therefore, we have the log base 10 of n of m is equal to y-intercept minus b times m. So, b is actually the slope of that line, slope of that best fit line. A is actually the y-intercept, the point at which the line is hitting the y-axis, right. So, which means that we may not need to actually make point by point this line, we may just need to know A and B of our source. If we can know A and B of our source, we know the magnitude recurrence relationship, because we know the general trend, and A and B are the only two numbers which are required to plot that line, right. So, therefore, the seismicity of any particular source is governed by these two numbers if you select this GR relationship model, right. So, small a and small b. So, this relationship, the validity of this relationship has been verified from observations of seismicity throughout the world. For any region, if you select the historical data, on average you will find that as the magnitude increased by 1, the number of earthquakes of that magnitude reduced by 10, right. So, the trend follows always straight line in log scale. So, again this is some example. Magnitude 8 is just two earthquakes, 7 is 20, 6 is 100, then 3000, then 15,000. So, roughly they are multiplying exponentially. Therefore, this GR model is also sometimes referred to as the exponential model. This is an example of how we actually constructed the magnitude recurrence relationship for different area sources while doing PSHA of Pakistan. So, just one example, this was a deep area source, and for that we constructed this line. So, you can see that all the dots roughly correspond to straight line, right. So, our data also confirm this GR model. Similarly, this is for another area source. So, I just show you one example. There were more than 20 area sources which we considered in the whole Pakistan. These are another MR relationships, magnitude recurrence relationships constructed while performing the PSHA of Southeast Asia, and again you can see that they follow a straight line trend. The frequency of occurrence is on y-axis, magnitude on x-axis, and obviously this would be the last point beyond which there is no data. So, they just make it down. So, the maximum magnitude which have occurred in this particular seismic source zone was magnitude 8.9 or something like that, right. So, you just truncate them at the maximum magnitude. It is not that the line will go on, right, you just truncate them. So, this is called truncated GR model. So, there were the different seismic sources developed for this particular PSHA, zone A up till zone K. So, for each zone you plot that curve, and you plot their comparison, and you directly know which is the active source, which is the less active source, what is the maximum magnitude which have occurred in particular source. So you can see this source, I don't know which one, maybe source maybe D, this one maybe. So this is the maximum magnitude which have occurred, 6.3 or 4, right? No earthquake beyond that. So this is a source which may not be able to produce a high magnitude earthquake in future. So similarly for fault sources also you develop this relationship, MR relationship, and generally you can use the same GR relationship for faults also, but there is also a characteristic earthquake model which you can use for faults. Characteristic mean that in area sources there is an assumption that the earthquake magnitudes are randomly distributed, and as you increase the magnitude their number reduce by 10 times. This is the assumption in area sources, and generally this assumption is true. For faults this assumption may not be true. There can be a fault which have some characteristic magnitude and it produce only the earthquakes of that magnitude, right? So for example, there can be a fault which produced more earthquakes of magnitude 6 than magnitude 5 and 7. In that case its line should not come down straight, right? It should be something like this, So more earthquakes occur in this range than less than that or more than that, right? So the line may not be straight always, it can be different also, and there is a model for that which is called characteristic model. So some faults may deviate from that line, and for that we have different other models also, but ultimately it is MR relationship, a relationship which is relating with the frequency of occurrence with the magnitude, right? So this is another example of some particular fault which is not following a straight line. You see it is like this, and then also the data which is used to plot that may have an uncertainty. So you may have a mean line, then 5th and 95th percentile also.